What's up, everybody? Welcome back. My name is Mr. Brown, and you're watching What's the Matter? Today we're going to continue our discussion on measurements and matter. And to do so, we are going to discuss precision, how to be grade A precise. We're going to discuss which numbers in a measurement are important and significant. And we're going to discuss when you make a measurement, how uncertain can you be about the measurement that you make. So grab your pen and pencil, pull out your keyboard, put yourself in that good positive vibe, and let's do it. Do you think it'd be more precise if I said I had about $1 or if I said I had $1.01? Or what about if I said it was about 4 o'clock or if I said it was 4:07 on the dot? In either case, the more digits I added to my measurement, the more precise my measurement became. The same would be true for scientific measurements done in the laboratory. The more digits I can add to my measurement, the closer to the actual value I am getting. So at the end of the day, just like a handyman, a scientist and the measurements they make are only as good as the tools that they are using. As science and technology advances, the tools that are used to make these critical measurements on the different matter that's out there in the world have become extremely sensitive. This allows for measurements of extreme precision, and those measurements can sometimes lead to extremely large numbers. To ensure that we can decipher between the numbers that are real and precise and the numbers that are estimated and guesses when we make measurements, scientists and mathematicians around the world use what's called significant figures. Significant figures allow us to be certain, accurate, and precise with the measurements we are taking. And because of that, we need to learn how to recognize significant figures in our measurements and also how to manipulate them. The main rule for determining the number of sig figs in any measurement, any value that you see, is that all non-zero digits, that's numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, are significant, no matter what the scenario. The question then lies, what about the zeros that we see in a number? Are they significant? Well, yes, sometimes they are, and no, sometimes they are not. And that is where our trick comes in. I'm not sure who thought of this or who developed this little trick, but I want to thank that person because I'm very grateful for being able to use this shortcut to determine the number of sig figs. And this shortcut is called the Pacific Atlantic rule. To use the Pacific Atlantic rule, first thing you need to remember is which side of the U.S. is the Pacific Ocean on and which side of the U.S. is the Atlantic Ocean on, because that is what tells us which side of a number we need to start reading from. If the decimal is absent, A, Atlantic, you will read the numbers starting on the right side of the value. As you read the numbers from right to left, the first non-zero digit you hit is a significant figure, and every other digit after that is also considered a significant digit, including the zeros. If the decimal is present, P for Pacific, you will read the numbers starting from the left side of the value. As you read the numbers from left to right, the first non-zero digit you hit is a sig fig, just like for Atlantic. And every other digit after that will be significant as well, including the zeros. In our first two examples, we see that a decimal is present, Pacific. So we start reading the number from the left side and start counting sig figs once we hit a real number, any of the numbers 1 through 9. In the first one, we start counting at the 3 and we count all of the digits after it as significant, meaning that the number 31.80 has 4 significant figures in it. In the second example, we start counting when we hit the 2 and count a total of 2 significant figures in the number 0.0020. In our other 2 examples, there is no decimal present. The decimal is absent, Atlantic. So that means that we read the number from the right to the left. In the third example, we start counting when we hit the 3 and count a total of 4 significant figures in the number 56,430. In the final example, we end up with only 1 significant figure in the value of 10,000. So by using the Pacific Atlantic rule, all I need to do when I see a number in order to figure out how many sig figs are in that number is determine if a decimal is present. Okay, so the more digits we have on a measurement, the more precise that measurement will be. Cool. So what about a very precise measurement of the count of cell phone users in the world? In 2016, the number of cell phone users in the world was about 5,149,000,000 users. Though the number is precise, and the more precise the better, that is a whole lot of number to be saying or writing down every time you need to refer to it. Many times, scientists are either measuring very, very small or very, very large quantities of matter. So of course they've devised a way to shorten up those numbers without losing any of its meaning. This expression that is used to represent and handle either very, very small or very large numbers is called the scientific notation. Every number that is in scientific notation will have 3 main characteristics that you will always see and you will always have to use. The first is this times 10. This shows that the value represented is in the power of tens. The second, and to go with the first, is an exponential number that is placed above the 10 to indicate the order of the expression. The exponent can be either positive or negative, and we will see shortly why and how this happens. The final part of the scientific notation template is the number in front of the times 10. And that number must always be greater than 1 and less than 10. This means you will never ever see a number in scientific notation that starts with a 0. Okay, so now that you can recognize a number in scientific notation, let's take a look at how we get there. To do this, you need to first determine which numbers are the significant figures in that value. Because when I turn it to scientific notation, I will keep all of the significant figures and I will drop all of the other ones. Next, I will move that decimal, and I like using a little hop fashion underneath each of the zeros, all the way until I reach my first non-zero digit, and then I will place that decimal after the non-zero digit. While you do this, while you hop in between the zeros over to the non-zero digit, you need to keep track of the number of hops, because that number is what you use for your exponent. Being that I move my decimal to the right, the exponent is going to be negative. On the flip side of that, what about when I have very, very large numbers, like the number of worldwide cell phone users? In that case, I will do the very same procedure, but in the opposite direction. Being that we moved the decimal to the left instead of moving it to the right, our exponent is now positive for the very big numbers. Okay, so now that you know how to count sig figs, how to take a number that is in standard notation and convert it to a number that is in scientific notation and back, I want you to pause the video at the prompt and give these examples a try. Now that we know how to take measurements, how to be precise with those measurements, and how to record the important numbers from a measurement, we need to finally understand what level of uncertainty will our measurements have. There are microscopes out there in the world that will measure something at the nanometer level. That is precision down to the 0.8 8 zeros and a 1. That is very precise and sensitive equipment, and it is very expensive too. You are measuring anything, especially something that small. The level of uncertainty can make a huge difference in your ability to repeat those measurements. So when a tool is used to make a measurement, the level of uncertainty is determined by how precise that tool can be. If you look at a ruler or the measuring cup that's in your kitchen right now, you will see a bunch of tick marks that help us determine the actual value of our measurement. Looking at this ruler right here, we see that there are big tick marks and little tick marks in between the big ones. If we wanted to measure a brick, we could see a value for the measurement using the big and little ticks. But we can get a little more precise than what the big ticks and little ticks provide us with. As mentioned earlier, we can only add one more digit to our measurement from what we can see with our tool. But this also brings some uncertainty into our measurement. Though we see roughly where the measurement is with no tick marks at that spot that we need them at, we need to consider the extra digit and estimate that carries uncertainty with it. Measurements in science is a science itself, but understanding them is critical for being able to understand and just sometimes believe in the matter that surrounds us. Well, that does it for today, everyone. I hope you had fun, and above all, I hope you learned something new. I'm your guide, your host, Mr. Brown, but remember, you matter because you're matter. So what's the matter? Thanks for watching. Have a glorious day.